Sun is destroying a hidden asteroid. Earth now passing through its fiery debris trail. In a remarkable cosmic discovery, scientists have revealed that our sun is actively tearing apart a massive asteroid, and Earth is now moving straight through the debris it left behind. This dramatic process has created a newly identified meteor shower that sky watchers can witness every year. Now let's dive deeper and explore every layer of this story on our AI podcast.
If you go out and look up into the night sky in late March and you happen to catch a shooting star, you're actually not looking at, just a piece of ancient peaceful space dust.
No, definitely not.
Yeah, you're actually looking at the active shrapnel of a massive celestial body that is, well, being essentially tortured to death by the sun.
That's a pretty intense way to put it, but yeah, it's accurate.
Right. The streak of light that you see is the violent, fiery end of a piece of cosmic debris. And today we are taking a deep dive into the source material behind a brand new, visually stunning meteor shower. And this shower is, quite literally, the active scene of a cosmic destruction.
It really is. It's a fascinating situation.
We're working from a recent astronomical paper today, and it details how the sun is actively tearing a massive asteroid apart, and how Earth, the very planet that you, listening, are sitting on right now, is passing directly through the middle of its debris cloud.
Yeah, and I mean, this research is so important because it bridges the gap between, those fleeting optical illusions we see up in our own atmosphere and the unseen extreme physics happening millions of miles away in the inner solar system.
Right. Totally unseen.
Exactly. The sheer mechanics of what is taking place out there fundamentally challenge how we even categorize objects in our solar system.
Which is wild to think about. So our mission today is to figure out exactly how scientists uncovered this hidden cosmic event using just a few streaks of light in the sky.
A very small amount of light, yeah.
Right. And we need to unpack the bizarre physical mechanisms of what they are calling a rock-comet. Plus, we're going to explore why tracking down this invisible debris-spitting asteroid is absolutely crucial for planetary defense. So, okay, let's unpack this.
Well, to understand the physics at play here, we really have to start with the physical evidence that's hitting our atmosphere. Because, for a really long time, this debris stream was intercepting Earth completely unnoticed.
Just totally under the radar.
Right, because the atmosphere is constantly bombarded by sporadic meteors. Just random space dust burning up without any coherent pattern at all.
Just background noise, basically.
Exactly. But researchers recently undertook this massive data analysis project. They were pulling from sky monitoring cameras all over the globe. And these cameras do not just record flashes of light. They measure the precise optical entry angle, the velocity, and the altitude of the burn.
So they have hard 3D data on these things.
Yes. But they were looking for, it's essentially a needle in a haystack of millions of data points.
Right, I mean millions.
Yeah, out of millions of atmospheric entries, they managed to isolate a highly specific cluster of just 282 shooting stars.
Wait, 282 out of millions?
Just 282. And when you calculate the 3D velocity vectors of those 282 meteors backward, adjusting for, Earth's own orbital velocity and atmospheric drag.
Because we are moving while we get hit.
Exactly. We're a moving target. So when you adjust for all of that, they do not point to random locations. Their trajectories converge. They all originate from the exact same point in space.
That is incredible. The technical term for that is the radiant, right?
Yep, the radiant.
It's like imagine you are standing in a pitch black field during a chaotic hurricane, and you're trying to track the path of millions of different raindrops.
That's a good way to picture it.
Right, and through pure mathematical modeling, you somehow isolate the exact trajectory of 282 specific drops of water. And you calculate their paths backward until you realize, hey, they didn't come from the clouds at all.
They came from a localized source.
Right, like a single spinning sprinkler head hidden somewhere in the dark.
Right.
That convergence point is the smoking gun.
It really is. And that three-dimensional tracking is what tipped the astronomical community off to the existence of a newly identified meteor stream. It's officially been designated as M2026A1.
Kitschy name.
Well, astronomers love their naming conventions, but the predictability of these orbital dynamics means that for you listening, this shower is actually going to be visible every single year between March 16 and April 7.
Which is awesome. But I should note, the sources make it clear that M2026A1 is not a dazzling, sky-filling light show like the Perseids, you are not going to go out and see 60 meters an hour.
No, no.
It is a very subtle shower.
Right, and what's fascinating here is that the volume of meteors is completely secondary to the astronomical significance of the data.
How so?
Because those 282 tiny flashes of light are our first, and currently our only, diagnostic signal that a massive rocky body is actively breaking apart somewhere nearby.
Wow.
Yeah, because we know the precise angle and speed at which those meteors struck Earth, we can actually mathematically reconstruct the entire orbit of the debris stream.
Oh, I see. And by mapping the debris stream, we map the path of the unseen object that left it behind.
Precisely. We track the breadcrumbs back to the source.
But the reconstructed orbit is really where this story takes a severe turn, based on the paper. Because this object isn't just, peacefully drifting through the cold outer solar system.
Not at all.
Its orbital path is highly elliptical. It swings terrifyingly close to our star. At perihelion, which is its closest approach, it comes nearly 5 times closer to the sun than Earth does.
Yeah, and the environmental conditions at that proximity are just brutal. We are talking about a literal cosmic kiln.
A kiln, wow.
But the destruction isn't just about the ambient temperature, It is driven by the extreme thermal gradient.
What does that mean practically?
Well, the object is rotating. So one side faces the relentless, unfiltered solar radiation, while the other side faces the absolute zero of deep space.
Oh, man.
So the surface of the asteroid undergoes these rapid, violent cycles of extreme thermal expansion and contraction.
There's actually a great quote in the research from Dr. Patrick Schober at NASA's Johnson Space Center. He said, "We are essentially witnessing a hidden asteroid being baked to bits."
Baked to bits is the perfect way to describe it. The rock is literally fatiguing under the stress. The constant expanding and shrinking, it compromises the structural integrity of the asteroid's outer crust.
Like dropping an ice cube in hot water and watching it crack.
Very similar, yeah. It creates these deep fissures. But thermal fracturing alone doesn't entirely explain the sheer volume of material being ejected into space.
Right. And here's where it gets really interesting, because the source material presents this massive contradiction. We know that typical meteor showers, the ones producing really prominent debris trails, come from comets.
Correct.
And comets leave trails because they're icy bodies. As they approach the sun, the ice sublimates directly into gas, spraying a massive glowing tail of dust and debris behind them. But the trajectory data here strongly indicates this parent object is a dense, rocky asteroid.
And rock does not sublimate.
Exactly. So how does a solid rock leave a debris stream like a comet?
It forces us to look at a relatively new and honestly very rare classification of objects. They're known as active asteroids, or colloquially, rock comets.
Rock comets, which sounds like an oxymoron.
It kind of is.
No.
To understand how a rock behaves like a comet, you have to look at the deep interior of the asteroid. These bodies were formed billions of years ago.
Right.
And many of them actually trapped volatile materials. So frozen gases and trace amounts of water deep within their porous rock matrices.
Okay, so the ice isn't on the surface. It is locked deep inside a solid rock vault, essentially.
Exactly. It's buried. But when the asteroid's highly elliptical orbit plunges it into that intense solar environment, the heat eventually penetrates deep down into the rock.
Oh, I see where this is going.
Yeah. Those trapped subterranean volatiles are suddenly flash heated. They sublimate from a solid directly into a gas, expanding violently.
And gas takes up way more space than ice.
So much more. The internal pressure builds exponentially until it literally exceeds the tensile strength of the surrounding rock matrix.
So the rock essentially bursts from the inside out.
The extreme internal outgassing forces its way through those new thermal fractures we talked about. And as the highly pressurized gas escapes into the vacuum of space, it violently carries dust, pebbles, and shards of rock out with it.
That is terrifying.
The rock structurally compromises, shedding material and forming a distinct glowing tail, so it mechanically mimics a melting comet. But it's driven not by surface ice, but by the extreme internal pressure of a baked asteroid.
The sun is essentially torturing this rock into pieces, and the result is this massive, invisible cloud of jagged shrapnel just drifting through the inner solar system.
And that debris stream has to go somewhere.
Right. Because of the intersecting orbits, our planet plows directly through this high-speed fallout.
We plow right through it, and the interaction between that shredded material and our atmosphere is governed by intense aerodynamic fluid dynamics.
Okay, break that down for us.
Well, when Earth's orbit intersects the M2026A1 debris stream, these fragments hit the upper atmosphere at speeds exceeding 24 kilometers per second.
24 kilometers a second. That is, at that speed, the physics of atmospheric entry go way beyond simple friction.
Oh, absolutely.
It becomes a matter of ram pressure. The fragment is moving so incomprehensibly fast that the air molecules in our upper atmosphere literally cannot get out of the way in time.
Right, the air just piles up.
The air in front of the rock is violently compressed.
And that rapid compression generates an immense amount of heat. It actually strips the electrons from the air molecules, creating a superheated shock wave of plasma.
Wow.
It is that incandescent plasma sheath that you see from the ground as a streak of light. The kinetic energy is so massive that the rock simply vaporizes inside the shock wave.
So by closely analyzing the specific light signatures of those plasma flares, the researchers were able to decode the physical properties of the rock itself.
Yes, exactly.
Because the altitude at which the meteor flares and how quickly it burns out acts as a sort of stress test.
It does. And the fragments from M2026A1, they occupy a very strange space in the data. They aren't behaving like typical meteorites. They fall into this sort of structural Goldilocks zone because, okay, a standard piece of asteroid debris is incredibly dense. It penetrates deep into the atmosphere before burning up.
Right, because it's solid rock.
Conversely, comet debris is incredibly light. It's mostly fluffy dust and ice particles that flare up and vaporize almost immediately upon hitting the very outermost layers of the atmosphere.
Like dandelion seeds hitting a windshield.
That's a great analogy. Now, the M2026A1 fragments flare up lower than comet dust, but much higher than standard asteroid rock.
Which means they're brittle.
Highly brittle. The light signatures prove that these fragments possess an intermediate fragility. They are heavily structurally compromised.
So what does this all mean? Why does the specific fragility of a rock hitting the atmosphere matter to you, the listener?
It's a great question.
Well, it fundamentally reframes what you were looking at when you go outside in late March. When you see that beautiful momentary streak of light, you are watching the final failure of a structurally compromised, heat-stressed rock.
Yeah.
You are witnessing the endpoint of a billions of years old bulk that was slowly baked, shattered from the inside out, and finally pulverized by the ram pressure of Earth's atmosphere.
And if we connect this to the bigger picture, identifying this specific intermediate fragility provides a crucial data point for materials scientists and astrophysicists.
Because we didn't have this data before.
Exactly. We have lacked concrete observational data on how massive space objects fracture, fatigue, and decay under extreme thermal stress. M2026A1 gives researchers the exact real-world parameters they need to refine their models of planetary decay and orbital debris generation.
Okay, so we have mapped the debris stream. We understand the thermodynamic processes of the cosmic kiln baking it into existence, and we know the exact velocity, ram pressure, and extreme fragility of the fragments.
They know a lot about it.
But all of this data points back to one glaring, honestly unsettling fact from the source material. The parent asteroid is entirely missing.
Yeah. That's the kicker. We have a mathematically perfect map of its orbit, but our telescopes have never actually detected the main body.
How does an active asteroid, a body massive enough to generate a yearly meteor shower, just hide from modern optical astronomy? I mean, we have amazing telescopes.
We do, but it uses the ultimate camouflage. The blinding glare of the sun.
Of course.
Because of its highly elliptical orbit, this rock comet spends the vast majority of its time deep in the inner solar system. The phase angle, which is the angle between the sun, the object, and Earth, means it is heavily backlit by the sun during the day.
So we'd have to look directly near the sun to see it.
And pointing highly sensitive optical telescopes toward the inner solar system is physically prohibitive. The intense visible light would irreparably fry the optics.
So it is hiding in our deepest observational blind spot. And I'm guessing it has likely been exhausted of any reflective surface ice by now.
Absolutely.
It's probably just baked into a dark, charcoal-like husk, which makes it even harder to spot against the blackness of space when it isn't completely washed out by the solar glare.
The astronomical community totally recognizes this severe vulnerability. It's actually why NASA is developing the NEO surveyor mission.
NEO, standing for Near Earth Object.
Yes, Near Earth Object. It's currently scheduled for launch in 2027. And rather than relying on visible light, which, as we said, is easily blinded by the sun, the INEO surveyor is designed to operate using advanced thermal infrared sensors.
Oh. So it isn't looking for the light reflecting off the rock. It is looking for the heat of the rock itself against the absolute zero of deep space.
Exactly. By detecting thermal emissions in the mid-infrared spectrum, a NEO surveyor can effectively bypass the visible glare of the sun. It'll allow us to finally peer into those massive blind spots and identify dark, potentially hazardous asteroids that are currently completely invisible to us.
Now, when I see the phrase potentially hazardous asteroids in the source material, I feel like it warrants a logical reality check.
Sure.
Because if we know this rock is incredibly brittle, if it is actively crumbling into pieces under thermal stress, and is so dark and diminished that we cannot even see it, is it genuinely a threat to Earth?
I mean, people hear brittle and think harmless.
Right. If a fragile rock comet hits the atmosphere, wouldn't it just vaporize instantly anyway? Why are we funding a multi-billion-dollar infrared telescope to track a crumbling rock?
Well, this raises an important question about the actual mechanics of planetary defense. Because the threat of an asteroid isn't solely dependent on it surviving all the way to the ground to create a massive crater.
Okay, then what is the threat?
The extreme fragility of a rock comet is exactly what makes it a really complex threat. If a massive, structurally compromised asteroid enters the atmosphere, the immense ram pressure we talked about doesn't just slowly burn it away.
Right.
The pressure exceeds the rock's tensile strength in an instant, causing the entire body to detonate midair.
Like an atmospheric airburst.
Yes, like the Chelyabinsk event over Russia back in 2013.
Oh, right, I remember that.
That was a relatively fragile, completely undetected asteroid that exploded violently in the atmosphere and never hit the ground. But the kinetic shockwave from the airburst shattered windows across an entire city and injured over 1,000 people.
Wow, just from the airburst.
Just the shockwave. Now imagine trying to deflect an incoming asteroid using a kinetic impactor, essentially ramming a spacecraft into it to change its course.
Which is our current main strategy for planetary defense.
Exactly. And if the asteroid is a solid, dense piece of iron, the kinetic impact shifts its orbit like a billiard ball. You hit it, it moves.
Makes sense.
But if you hit a heavily fractured, heat-stressed rock comet,
Oh, wait. You don't deflect it, you just shatter it.
you shatter it entirely. You turn a single, trackable bullet into an unmanageable, unpredictable shotgun blast of high-speed debris.
And it's all still on a collision course with Earth's atmosphere.
Exactly. That is why studying M2026A1 and finding its missing parent is so critical. We aren't just categorizing rocks up there, we are actively testing our planetary defense models. We absolutely have to understand the specific structural integrity of these baked asteroids before a truly dangerous hidden object heads our way.
The source material takes what seems like, just a piece of cosmic trivia and really elevates it to a matter of planetary survival.
It really does.
I mean, we started this deep dive with an anomaly, 282 specific streaks of light isolated from millions of data points.
Which is still an incredible feat of data science.
Oh, absolutely.
Yeah.
And tracking those velocity vectors backward revealed an invisible rock comet, this ancient vault being brutally baked and fractured from the inside out by extreme solar radiation.
Yeah.
And as Earth casually intersects that celestial shrapnel at hypersonic speeds, we get the M2026A1 meteor shower. A glowing roadmap leading to an unseen, potentially hazardous object hiding right in the sun's glare.
The entire system is incredibly dynamic. We tend to view the solar system as this, static, peaceful clockwork, but it is a continuously evolving, highly destructive environment.
So your mission is simple. Between mid-March and early April, find a dark location away from city lights, let your eyes adjust, and just look up.
Give it a little time.
Yeah, be patient. And if you are patient enough to catch a streak from the M2026A1 shower, you will know the terrifying physics behind it. You are literally watching a hypersonic plasma shockwave vaporize the remains of a fractured world.
And as you scan the dark for those falling stars, consider the broader implications of what this discovery proves.
Which are what?
Well, we now have undeniable evidence that the sun's intense thermal gradient is slowly, methodically tearing massive rocky asteroids apart right in our orbital neighborhood.
Right.
And we know that these disintegrating bodies are completely shielded from our view by the sun's blinding light. So what does that mean for the countless other undiscovered objects hiding in our solar system's blind spots?
Oh, man.
Could there be an entire unseen graveyard of fractured worlds orbiting right on our cosmic doorstep, quietly shedding high-speed debris paths we haven't even noticed yet?
Okay, one question for you. Considering that Earth is currently passing through the debris field of a crumbling asteroid. What are the potential risks, if any, to our planet? And how do scientists ensure that such events remain harmless to life on Earth? Don't forget to comment it. Thanks.